So, we are discussing the problems on statistical thermodynamics. So, the problem number 6 is consider two moles of a monoatomic ideal gas at 10 bar pressure and a temperature of 300 Kelvin in an isolated system. While remaining isolated, the gas is expanded into a vacuum from a volume of V 1 equals to 1 liter to V 2 equals to 10 liter. Calculate delta S and Q reversible for the process. And we need to use statistical, mechanical concept only. So, we are not allowed to use thermodynamical equation here. We need to consider statistical mechanical concept here, and this problem is based on Sackur-Tetrode equation that we discussed. So, from Sackur-Tetrode equation, we know S is n kb So, Sackur-Tetrode equation, from Sackur-Tetrode equation we know the expression of entropy S is n times kb, n is the number of particles, kb is the Boltzmann constant, and then you have logarithm of twice pi m kbt by h to the 2 to the 3 by 2 v by n and e to the 5 by 2. And the information provided here are like temperature is 300 Kelvin and number of particles here is 2 times Avogadro number, because there in the problem it is saying that we have to consider 2 moles. So, what is delta S? So, delta S is twice Na Kb ln V2 by V1. Since other terms are constant, so we can clearly write change in entropy is 2 times Na times Kb logarithm of V2 by V1, and if we solve this one we get 2 times R ln V2 by V1, and we get delta S is 9.21, and we get the value of delta S. So, delta S here is 9.21 calorie per Kelvin. Once we get delta S, we can easily calculate Q reversible, because Q reversible time Q reversible by T gives us delta S, and temperature is given 300 Kelvin. So, Q reversible is 2.76 kilocalorie. So, this is very simple problem, but it uses the Sackur-Tetrode equation. Next, we will discuss another interesting problem. The problem says the partition function for Einstein's proposed model for atomic crystal can be written as Q is e to the minus beta u naught e to the minus beta h nu by 2 by 1 minus e to the minus beta h nu. Where nu is the frequency with which the atoms vibrate about their lattice positions and u naught, which is independent of temperature, is the sublimation energy at 0 Kelvin temperature, or the energy needed to separate all atoms from one another at 0 K temperature. Calculate the molar heat capacity of an atomic crystal from this partition function. So, this problem is little bit lengthy, but it is very simple problem. It says the partition function for Einstein's proposed model for atomic crystals can be written as Q is e to the minus beta u naught e to the minus beta h nu by 1 minus e to the minus beta h nu, where nu is the frequency with which the atoms vibrate about their lattice positions, and U naught, which is independent of temperature, is the sublimation energy at 0 Kelvin temperature, or the energy needed to separate all atoms from one another at 0 Kelvin temperature. Calculate the molar heat capacity of an atomic crystal from this partition function. So, partition function is given and we need to calculate heat capacity. So, next thing we need to do is we need to calculate average energy. Once we get the average energy from the partition function expression, we can easily calculate heat capacity. So, we will use this partition function to calculate the average energy. So, the partition function Q is e to the minus beta h nu beta u nu e to the minus beta u naught e to the minus beta h nu by 2 by 1 minus e to the minus beta h nu. So, what we would do actually, we would use for the partition function expression, you consider e to the partition function expression is now little bit modified. So, we use q is e to the minus beta u naught e to the minus beta h nu by 2 by 1 minus e to the minus beta h nu, and the whole thing is powered by n. So, this is the partition function expression. So, ln q, now we have to consider molar heat capacity. So, heat capacity, molar heat capacity we need to calculate. Molar heat capacity. So, molar heat capacity means we have to consider n is number of is Na here. So, we get q, we have q. So, we can take logarithm of q both sides, we get now what we got ln q, the expression for ln q. Now, what we need to do, we need to differentiate q with respect to beta at constant n and v. So, the first term is independent of temperature, we are differentiating with respect to temperature. So, the first term gives us 0, second term also gives us n h nu by 2. Now, the third term we have n ln 1 minus e to the beta b to the minus beta h nu. So, if we differentiate this with respect to beta, we get and del ln q by del beta is nothing but minus of E average So, we get E average is n h nu by 2 minus n h nu by e to the plus e to the h nu by k b t minus 1. So, this is the expression for average energy. So, we have got the expression for average energy. Now, we can calculate molar heat capacity by considering n equals to Na. Okay, so, the expression for energy we have now is E is n h nu by 2 plus n h nu by e to the h nu by kBt minus 1. So, Cv is del E average by del T at constant volume. So, it gives us, the first term gives us 0 and the second term, if we differentiate, we get so, if we differentiate it, the expression of E, we get first term gives us 0 and the second time if we differentiate we get n h nu by e to the h nu by kBt to the 2 times minus 1 times e to the h nu by kBt and times minus h nu by kBt to the 2. So, we get Cv is n h nu by kB to the 2 times T e to the h nu by kBt by e to the h nu by kBt minus 1 to the 2. Now, molar heat capacity means n equals to Na, we write Cv is Na times Kb our molar heat capacity Cv bar is Na times Kb gives us R. So, R h nu by kBt to the 2 e to the h nu by kBt by e to the h nu by kBt minus 1 to the 2. So, this is the expression for molar heat capacity. This is straightforward. This was a very straightforward problem, but one really has to work out. Now, the third one we will discuss for problem number 8 is the average kinetic energy is 3 kBt by 2 of hydrogen gas or hydrogen atoms in a stellar gas is 1 electron volt. What is the ratio of the number of hydrogen atoms in the second excited state to the number in the ground state the energy levels of the hydrogen atoms are epsilon n is minus alpha n to the 2, where alpha equals to 13.6 electron volt, and the degeneracy of the nth level is 2n to the 2. So, this problem states the average kinetic energy is 3 kBT by 2 of hydrogen atoms in a stellar gas is 1 electron volt. What is the ratio of the number of hydrogen atoms in the second excited state to the number in the ground state, means n equals to 1 state? The energy levels of the hydrogen atoms are epsilon n equals to minus alpha by n to the 2, where alpha is 13.6 electron volt, and the degeneracy of the nth level is 2n to the 2. Now, the information provided here are for ground state means n equals to 1, the value of energy is minus 13.6 by 1 to the 2 electron volt gives you minus 13.6 electron volt, and degeneracy of ground energy level, we say this is G1 is 2 times 1 to the 2, so this gives us 2. Now, for second excited state, so for second excited state n is 3 not 2, remember that, because we have the ground state, then first excited state, then second excited state, and the ground state we are saying n equals to 1. So, for second excited state n equals to 3, the energy value epsilon 3 is minus 13.6 by 3 to the 2 electron volt, or minus 13.6 by 9 electron volt. And the degeneracy of second excited state, we say this is G3. So, this is nothing but 2 times 3 to the 2, so this gives us 18. And what we need to calculate? We need to calculate the ratio of number of hydrogen atoms in the second excited state to the number in the ground excited state. So, we need to calculate what is the value of N3 by N1, where N3 is the number of hydrogen atoms in the second excited state, and N1 is the number of hydrogen atoms in the ground energy level. Now, from Boltzmann distribution we know N3 by N1 is G3 by G1 times e to the minus beta epsilon 3 minus epsilon 1. So, N3 by N1 is G3 is 18, G1 is 2 times e to the minus epsilon 3 is 13.6 by 9, and we have the minus sign here, and then we have this is 13.6 times beta. So, we have N3 by N1 is 9 times e to the 13.6 times 9 minus 13.6 by 9, this is in electron volt, times beta is 1 by kBt. Now, it is given that 3 by 2 kBt is 1 electron volt. So, kBt is nothing but 2 by 3 electron volt. So, we get N3 by N1 is 9 times e to the So, if we carry out this, we get N3 by N1, the value of N3 by N1 is 1.2 times 10 to the minus 7. Okay, so this is again a very simple problem, but it's bit you need to carry out little bit. Now, the next problem is based on is taken from rotational partition function. The length of the bond in oxygen molecule is 1.207 angstrom. Determine the rotational temperature, and the rotational partition function for oxygen at 300 Kelvin temperature. It is given molar mass of oxygen molecule or oxygen is 32 gram. So, it is pretty straightforward. It says the length of the bond in oxygen molecule is 1.207 angstrom. Determine the rotational temperature and the rotational partition function for oxygen at 300 Kelvin. And the information provided is like molar mass of oxygen is 32 gram. So, you need to first know, because while discussing rotational partition function we considered symmetry number. So, symmetry number we need to consider here. So, oxygen molecule is a homogeneous diatomic molecule. So, the symmetry number is 2 for oxygen molecule. For oxygen molecule, this is very important. For oxygen molecule, the symmetry number is 2, because this is homogeneous diatomic molecule. Next, what we need to do, we need to calculate rotational temperature. So, rotational temperature theta is h to the 2 by 8 pi square I kb. So, value of h kb, these are known, we need to calculate I, moment of inertia of oxygen molecule. So, I is mu r square. So, m1 m2 by m1 plus m2 r square, and here m1 equals to m2. So, we can write m r square, and then we have half term here, because m1 is equal to m2 equals to m for oxygen molecule. So, I is half, and mass of oxygen molecule is 32, and here m is mass of a single atom. So, 16 we need to consider, 16 times 10 to the minus 3, this is in kg by Avogadro number, 6.023 times 10 to the 23, this is m, and this is r is 1.207 times 10 to the minus 10 kg meter to the 2. Okay, so, if we calculate this, we get the value of moment of inertia is 1.937 times 10 to the minus 46 kg meter to the 2. So, this is the value of moment of inertia. Now, we can calculate rotational temperature. So, rotational temperature theta is h to the 2 by 8 pi square I kb. So, theta is 6.627 times 10 to the minus 34 by 8 times 3.14 to the 2 times I is 1.937 times 10 to the minus 46 times kb is 1.38 times 10 to the minus 23. This is in Kelvin. So, if we carry out, we get theta is 2.08 Kelvin. So, this is the value of rotational temperature, and rotational partition function Q rotational is T by sigma times theta rotational. So, Q rotational is, temperature is 300 Kelvin and sigma is 2 and theta is 2.08. So, you get 300. Q rotational is, so you get Q rotational is 72. Okay, so this is the value of rotational partition function. Next, we discuss one problem based on vibrational partition function. Consider the molecule N2 for which theta vibrational is 3397 Kelvin. A spectroscopic measurement of the populations of n equals to 0 states shows Pn equals to 0. So, here Pn is the probability of nth state is 0.75. So, Pn is the probability. of n state, or Pn is the, maybe we can write it in different manner. So, Pn is the, where Pn is the fraction of molecules in energy level n. So, here P naught is, we say P naught, not P n, we said P naught is 0.75. So, what is the temperature of the gas? So, this problem states, consider the molecule N2 for which the theta value of theta for which the value of theta vibrational is 3397 Kelvin. A spectroscopic measurement of the populations of n equals to 0 states shows 0 levels, you consider here, shows P naught equals to 0.75, where Pn is the fraction of molecule in the energy level n. What is the temperature of the gas? Okay, so from we know vibrational partition function, we know the value of, we know the expression. How do you solve it? So, hint here is, you know what is the expression for Pn, okay, from vibrational partition function. So, once you get Pn, the value you substitute, then value of Pn is 0.75. So, you have some expression here. Once you substitute this, you calculate the value of temperature. So, this is a very simple problem. So, you can always carry out. So, I am just skipping that one. So, next problem is, this is very interesting problem. A three-dimensional harmonic oscillator has energy levels where N1, N2, N3 can be 0, 1, 2, 3, etc. Calculate the ratio of the population of energy levels having energies h nu by 2 and 9 h nu by 2 at T Kelvin temperature. Prove that when h nu equals to 1.2 times kBT, the population of 9 h nu by 2 level will be half of that 7 h nu by 2 level. So, this problem says a three-dimensional harmonic oscillator has energy levels epsilon is n1, n2, n3 equals to h nu times n1 plus n2 plus n3 plus 3 by 2, where n1, n2, n3 can be 0, 1, 2, 3, etc. Calculate the ratio of population of energy levels having energy 9 h nu by 2 and 7 h nu by 2 at T Kelvin temperature. And we need to further prove that when h nu equals to 1.2 kBt, the population of 9 h nu by 2 level will be half of that of 7 h nu by 2 level. So, how to solve this problem? Next. Okay, so, it is given the energy of a three-dimensional harmonic oscillator is h nu times n1 plus n2 plus n3 plus 3 by 2. Now, when epsilon value of epsilon is when epsilon is 9, first we consider 7 h nu by 2. So, 7 h nu by 2. So, for epsilon 7 h nu by 2, the degeneracy we need to calculate. So, the degeneracy is, suppose G is 7 h nu by 2 we consider. So, consider here, for epsilon equals to 7 h nu by 2, the degeneracy is G 7 h nu by 2, and for epsilon is 9 h nu by 2, the degeneracy is G 9 h nu by 2. So, how to calculate degeneracy? Next thing is, so when epsilon equals to 7 h nu by 2, so we can write 7 h nu by 2 is h nu times n1 plus n2 plus n3 plus 3 by 2. So, it gives us n1 plus n2 plus n3 is 2. So, we can have n1 equals to 2, n2 equals to 0, n3 equals to 0. This is one possibility. Second possibility is n1 equals to 1, n2 equals to 1, n3 equals to 0. Third possibility is n1 equals to 1, n2 equals to 0, n3 equals to 1. Fourth possibility is n1 equals to 0, n2 equals to 2, n3 equals to 0. Then fifth possibility is n1 equals to 0, n2 equals to 1, n3 equals to 1. And the last possibility is n1 equals to 0, n2 equals to 0, and n3 equals to 2. So, 6 different possibilities are there. So, the degeneracy, so is 6. So, we have got the degeneracy of energy level having energies 7 h nu by 2. Next, we calculate for epsilon equals to 9 h nu by 2. We will do the similar, we will perform similar exercise here also. So, we can write like before is so, this gives us n1 plus n2 plus n3 equals to 3. So, how many possibilities we will have? So, we can have n1 equals to 3, n2 equals to 0, n3 equals to 0. This is one possibility. Second possibility is n2 equals to 2 into 1 n3 0, and then we have n1 equals to 1, n2 equals to 2, n3 equals to 0, then we will have n1 equals to 2, n2 0, n3 1, then n1 1, n2 0, n3 2, then we have n1 0, n2 3, n3 0, then n1 0, n2 2, n3 1, n1 0, n2 1, n3 2, and then we have n1 0, n2 0, n3 3, and then we have another one is n1 1, n2 1, n3 1. So we have 3, 6, 10 possibilities. So we get G 9 h nu by 2 is 10. Okay, so population of energy level having energy. So suppose the population of energy level having energy (7 h nu by 2) is n 7 h nu by 2, and the population of energy level having energy 9 h nu by 2 is n 9 h nu by 2. So we can write n 7 h nu by 2 by n 9 h nu by 2. That's what we need to calculate. N 9 h nu by 2 is G 7 h nu by 2 by G 9 h nu by 2 e to the minus beta 7 h nu by 2 minus 9 h nu by 2. So write n 7 h nu by 2 by 9 n 9 h nu by 2 is 6 by 10 e to the beta h nu. So we get n 7 h nu by 2 by n 9 h nu by 2 is 3 by 5 e to the h nu by kBt. So this is the ratio of population of epsilon equals to 7 h nu by 2 and epsilon is 9 h nu by 2 energy levels. Now the next part, when h nu is 1.2 times kBt, we get n 7 h nu by 2 by n 9 h nu by 2 is 3 by 5 e to the 1.2. So, this gives us n 7 h nu by 2 by n 9 h nu by 2. The value of this one, if we carry out, we get, okay. So, we get this value is 2. If we further carry out this, okay. So, this is the second part. So, it says that the population of energy level having energy 9 h nu by 2 is half of that for energy 7 h nu by 2. Thank you.